did I give you these yesterday?
True.
I did. Wonderful.
They were back there.
Good. I thought I did, but I wanted to make sure. Okay. That is great news. Today we have a quiz review because we have quiz tomorrow. Here it is. This is one I think you should be able to knock out of the park. So please do, so I can put it in the grade book for your last quarter.
Whoa, come on, Alan.
If you don't feel like you're going to be able to knock it out of the park, come see me before after school. I have extra time today. I have a little bit more than I usually do.
I'm coming in early tomorrow.
Early tomorrow works as well.
Yeah, I think I am too.
I'm just going to stay here all day.
Is Katie here today?
No. She's at
Yikes.
I think I'm just going to sit here. I really want to come school there.
Yeah, but you did.
Wow, that was sad.
All right. Should be back there. I haven't touched it in a while.
Oh.
It's not out of Staples, is it? That's right. It's the most wonderful time.
Ow!
What is the cloud? You're not.
All right.
Where is everybody?
I can
I'll take some quick attendance.
I've been sat behind this for 4 minutes. Let's go.
China's here. She's not here. Where's Aiden?
Aiden?
The ortho bus.
Yes.
Today's an ortho bus day?
Yeah, it's so...
It happens all the time, so they get the rubber bands tied together? Is that what happens?
It's a rubber band thing.
Or whatever?
Adjusted.
Adjusted?
I think.
That is adorable. What school does this?
They get jacked up.
Right? That's right.
Let's go
Put
Carter.
him on the jack, get him in the chair.
Staple.
Does anybody else want
It's a terrible day to miss.
It's fine.
Erica's gone for that as well.
What? It's their fault.
Where's Nancy? Oh, Nancy's right there. Stop blocking Nancy.
Okay, let me sit down.
Let's
So
go
you're running down the hallway right
Carter.
there.
Let's go
With your, like,
Carter.
with your overalls, you look like you're like Super Mario.
Let's go Carter. Let's go.
Oh my god.
Danny.
All right. Cool.
That was hilarious.
Let's go. That's a 3-star.
All right, so
Now that I think of it,
we'll do a lot.
That's a 3-star, Danny.
All right. What's up, nerds? Today is your review for the quiz. If you're watching along at home, which you should be if you're at the orthodontist, right? Pull out that phone. Watch right now.
Let's go, Danny.
Let's do it. Let's do it.
3-star.
Here's a quiz review. Quiz tomorrow is basically going to be this. Some stuff won't be on there, right? That's how the stuff works, right? I take all your homework and I smash it together, change some of the numbers, and then to make the quiz, I change the numbers again, and then delete some of the questions I don't really like that are more of a waste of your time. You do need to know all this crap. That's why I put it in the review guide, right? You do need to know it all. However, if you know what a transversal is, right, I can test that on a more thorough question than just asking you what is a transversal, right? So, I'm not saying that won't be on there, but it might not. I don't know. I haven't made it yet, right? So if I can, do 2 birds, 1 stone, so to speak, 2 carrots, 1 knife, I will. That's how it works. So let's get into it. I'm going to skip page 1. So if you'll open your hymnals to page 2. No, I always make them the day before. I make this Wednesday night. And then I take this and cut this stuff down Thursday night. No, I'm not. I don't know what's going to be on the quiz until we've covered it in class, right? If you guys are struggling with it, then the quiz is different. If you guys are doing fine, then this is what we do, right? Depends on how stuff goes. So, using only corresponding angles postulate, vertical angles theorem, linear pair theorem, definitions, and any of the properties of quality, complete the following proofs. Basically what that means, okay, words are hard, math is easy, is that you are not allowed to say 3 and 6 are congruent because of alternate interior angles theorem. Done. Right? We're not doing that. We are proving alternate interior angles theorem for number 2.
I didn't get
Page 2? It's not on there?
Oh, it is.
Oh, okay. Good. All right. All right.
But that's the same diagram on the front page, isn't it?
It's similar. All right. So, I reuse things when I can, but I don't think I actually reused that one. I think I actually did it separately. Nope. They're differently spaced. The one on the front has 4, 3, and this one has 3, 4. Also, the lines are different. They definitely are. I could have reused it, but I didn't. So anyway, we're on number 2, page 2. So we're not allowed to just say corresponding, or we're not allowed to say just alternate interior angles theorem and call it a day, right? That'll be later. For now, we're proving that. So we're allowed to use cap, VAT, and LPT. We're allowed to use definitions if necessary. You probably won't have to use very many. And then properties of equality, like substitution is going to be a big one, right? So here we go. Prove 3 is 6. I'm going to do it in dark blue. 3 is 6. So here's what I would do. I would say, look, 3 is the same thing as 7 by cap, right? Corresponding angles. They're both in the bottom left corner. Remember, corresponding angle says that angles are corresponding if they're in the same relative location. Well, if you look at this intersection, that's bottom left corner. This intersection, that's bottom left corner. So 7 and 3 are corresponding. Corresponding angles postulate says if they're corresponding, which they is, then we should be able to say they're congruent, right? If the lines are parallel, which, again, they is. So we're going to write down, given L is parallel to M, right? If L isn't parallel to M, we can't use any of the corresponding angles postulate. We can't use any of that stuff, right? What?
We have to write them in the test. Given LM.
Because if it was not given to us, we wouldn't be able to do it, right?
Yep.
Also, it's a free point. So for each of these, you're going to write, given L is parallel to M. I called them L and M. You can call them whatever you want. So I would write that just right off the bat.
I'm gonna write my test in cursive.
Dear God. All right. So, given L is parallel to M,
Did you always make those?
we know that 3 and 7 are congruent.
Let's write our entire test in one equation.
No, please no. 3 and 7 by cap, corresponding angles postulate. There's our reason why, right? Again, corresponding angles postulate says if the lines are parallel. So we have to show that the lines are parallel first, right? Not all corresponding angles are congruent.
Did you make that slightly larger?
Can you find my quiz?
Yes.
My test?
Thank you.
Can you?
Not yet.
You already have class.
I don't know why I'm missing it. Did you actually sign your name to it?
No, I didn't.
Hey,
You told me though. I remember.
I didn't
You
ask.
passed it on. You like did it. You forgot to put your test name on it.
And you never did?
I don't think I-
Great, wonderful, that'll work. All right, so if these two are parallel, right, then the corresponding angles are going to be congruent, right? If those are parallel, then those corresponding angles are congruent, right? Ding, ding, good to go. But what if they aren't parallel? Here's two lines that are not parallel,
Oh, that was Smith.
right? They're not. They're eventually going to intersect, but I'm not going to make them intersect just to save you the time. Here's my transversal. It's a transversal because it cuts those two lines. Now, the corresponding angles would be here and here, 1 and 5, right? Are they going to be congruent? No. So that's why we have to say, hey, look, these are parallel. Now we're allowed to use stuff like cap, okay? That opens up the door. So now 3 and 7 are congruent. What's the relationship between 7 and 6? Vertical, right? And now I win because if 7 is 6, then I can switch them out and say that 3 is going to be congruent to 6. Now, that's the strategy I used, right? There are lots of things I know about 3. Like 3, whoops, tell me you can't see it. 3 is congruent to 2 by vertical angles. Autumn, scoot up today. You have no reason to sit back there. Sit behind him. 3 and 2 are congruent by vertical angles.
I'm not the one with the vision problem. He asked.
Okay, look, I don't care whether you do it or not. Just do it or don't. Sure you are.
Same shirt.
All right, so
Say what you're
3 and 2. Can you see everything? Okay, so I'm going to do a proof. You said that you're okay. Now, I'm going to define okay. The definition of okay is being able to see what I'm doing, right? So proof by contradiction, you can't see what I'm doing, therefore, you are not okay. Swag box.
Conjecture.
Now, you don't have to do anything because, like, you do you, right? But, like, you're a dummy if you don't. There we go. Okay. Xavier, would you like to join us up here, too, so you can actually see what's going on?
Define it to me.
Do you want me to move one more seat?
I don't want you to do anything. I just want you to do what's best, I suppose. So I guess I do want that.
Can I sit closer to you?
You do you. No. 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 Okay? No. I don't want to smell any of it. I don't think that's true. We talked about first hour of running this like a talk show where I have like a guest here and then like, you're over on the side as my like, when I run out of questions, you bump in, right? Like, got a great show for you tonight, Our guest tonight is whatever, right? And it could be like corresponding angles. All right. 3 and 7 are congruent. I also know that 7 and 6 are the same dumb thing. How do I know 7 and 6 are congruent? Vertical angles by VAT, vertical angles theorem. Again, vertical angles, we actually don't need the lines to be parallel, right? Any two lines that intersect, no matter what's going on, top and bottom are going to be congruent, left and right are going to be congruent. So 7 and 6 are good to go. My U's have a tail. My V's have a front thing. I don't know. It's a little curve. So now check it out. If 7 is the same thing as 6, they're interchangeable, right? So I'm going to write 3 is congruent to 6. I'm going to switch out the 6 and the 7, right? I don't need an arrow there. I'm just doing that to show you. So 3 is the same thing as 6 by substitution. And now we're done. Swag box.
That makes sense.
Right?
It wasn't
3 is 7 by cap.
like 2 days
7
ago.
is 6 by vertical angles. Switch out 6 for 7. We win.
Do you know what that means? Okay.
Yeah, he's never heard Blueface though. Have you listened to Blueface yet?
No comment. All right. Angle 1 and angle 8.
He listens to him all the time. Stop
Follow me on Spotify.
How can I sleep off the one?
1 and 8. How are we going to prove that they're congruent? Because that's number 3. I'm going to number 3. How do we prove them congruent? Yeah. What's your strategy? 1 and 5, then 5 and 8. It's the same dumb crap, right? 1 and 5 is cap. 5 and 8, vertical. Done. Same dumb thing. I'm not going to write it. Now, could you have done it another way? Who can find another way?
I like this one.
Got another one? Come on, think of another. Xavier.
1 and 4, and then 4 is 5. With 8,
Yep. To go 4 to 5, we'd have to have alternate interior angles, and we're not allowed to use that, right? Got another one?
We could say that 4 is equal to 8 through cap.
Yep.
And then say that 1 is equal to 4 through that, and then substitute that.
So what Xavier said, but backwards. Yep. You can either do the cap first and say 4 and 8 are the same, and then vertical, 1 and 4, right? Or you can do the vertical first, 1 and 4, 4 and 8, right? Same dumb crap. Let's look at number 4. It says 4 and 7 supplementary. So here's 4. Here's 7. So what's your strategy? We need to say they're supplementary. Which theorem allows us to say things are supplementary, right? VAT is vertical angles theorem. That says they're congruent, right? Corresponding angles are congruent as well, right? So LPT, linear pair theorem, is going to get us supplementary. So let's get that first. Again, you could do things in reverse order, like we discussed, right? But you're going to hit that linear pair theorem at some point. So let's look at angle 4. Angle 4 is a linear pair with 2 angles, 2 and 3. Now, does 2 or 3 relate to 7 better? 3 does, right? Because 3 and 7 are cap, right? So let's say 4 and 3 are linear pair, right? Would it be valid to say 4 and 2 are? Sure. Just wouldn't be as helpful, right? So I'm going to say 4 and 3 are linear pair. Angle 4 and angle 3 are linear pair, right? So they're supplementary by linear pair theorem. Now, last week we had to say they're a linear pair by definition, right? And after we've established that they're a linear pair, then we used LPT. Now, we are in a time where you guys know that 3 and 4 are linear pair just by looking at it. So I don't need you to prove that to me, okay? 4 and 3 are supplementary by LPT. Good enough for me. Okay? Linear pair theorem says they're supplementary. Don't tell me they add up to 180. That's the definition of supplementary. So now we know they're supplementary. Now what do we know about 3 and 7? Congruent by cap.
They're on the same line.
They are, but they're not a linear pair. They are collinear. 3 and 7 are, but they're not a linear pair. Collinear is not that special. Now check it out. 3 is the same thing as 7. So instead of writing 3, I'm going to write 7 there. That's all. So angle 4 and angle 7, again, don't write a congruency sign. Don't get in the habit of just writing congruency whenever you have 2 angles. And angle 7 are supplementary. That's what we want to show, right? 4 and 7 are not congruent.
What's up?
By substitution. S-U-B-S. And we're done. Swag box. Are you smelling what I'm stepping in?
Yes, of course. Actually, no, I dig smelling it.
Wonderful. Yeah, it doesn't matter which order you do it in. We discussed that. 4 and 3, supplementary. 3 and 7, congruent. So if 4 is supplementary with 3, it must be supplementary with 7. Bam. How do you feel? Dece?
Better since I sat closer.
Oh, wonderful. Close to the room mic as well, so everybody can hear your comments. All right, 2 and 8 supplementary is the last one.
That's smaller.
Let's take a look at 2 and 8. 2, 8, those two. Ah, same side exterior angles, yeah? So 2 and 8 supplementary. What would be your strategy? Someone tell me what they're going to do. It's okay. I'm going to hit it again. First of all, let's get the supplementary part out of the way. 2 is supplementary with 2 angles. Angle 1, right, because they make a linear pair. And angle 4, because they make a linear pair. You see that, Autumn? That 2 and 4 are a linear pair, so is 1 and 2. Oh, I thought you said you didn't get it. You do get it. Wonderful. Excellent. Fantastic. Fantastic. Wonderful, wonderful, wonderful. Wonderful. Erica, you're here! I marked you absent. I thought you were on the braces bus. Did they not call it the braces bus? Because they should call it the braces bus.
Sounds better.
Erica, do you have braces?
No.
Okay, I'm sorry. I don't know why I thought you did.
Now you're assuming.
I'm assuming. You know what that does to us? It makes it out of and, right?
Yeah.
So now, 1 and 2 and 2 and 4 are both supplementary. Now, which one's going to be more useful if we want to talk about 8? 2 and 1 or 2 and 4? 2 and 4 because 4 and 8 are cap, right? So 2 and 4 are sup by LPT. 4 and 8 are congruent by cap. So 2 must be supplementary with 8. Do I need to write it? I won't do it! It's the same thing here. It's just 2 and 4 instead of 4 and 3. And then 4 and 8 instead of 3 and 7. Be careful how you say that. 4 and 8.
4 and 8.
Mucho cuidado, por favor. Señor Mao.
Now you sound like Steve from Minecraft again.
Yeah?
Again.
Wow. Wow. That's all I've ever wanted to
You
be.
said cool like 4 times.
That's all I've ever wanted to be. All right. Given measure of angle, we're on the 3rd page now. This should look very similar to your homework. The only thing I changed is that they add up to 65, or they equal 65 instead of 55 or whatever it was. Okay. They tell you that AFB and EFD are 65. So I'm going to label those 65. You better bet I'm going to give you a different diagram tomorrow, right?
Better bet.
I will.
I don't bet. You better bet.
Yeah. You better, you
No,
better,
you
you
better.
bet. It's a good song. All right. It tells you that points BFD and EFC are collinear. That just means that those guys are lines, just in case there's any confusion, right? So those are 65. It says find BFC and DFE in their relationship and then label the angles, right? So BFC, Brian's Fried Chicken, and DFE down here, the pink angle that we've already done. What's the relationship between these two angles? Vertical, all day, baby, right? Which means they are congruent by vertical angle theorem. So vertical angles, they're both 65. Cool, cool, cool. All right, BFA is this pink angle, and DFE is this pink angle down here. They're congruent, but that doesn't mean they're vertical, right? It's just a coincidence. Are they a linear pair? These two. No. Why not? Because there's an angle in the middle, right? If they were a linear pair, then linear pair theorem would apply, and they would be supplementary. Is they? They is not. Okay? So they're not.
Neither.
So it's neither.
Neither.
BFC, that's this one, Brian's Fried Chicken, and CFD, this one right here. We'll do that in green.
LP.
These two, linear pair, yeah? They sit on BFD. There's the two angles make up the whole thing. So they must be supplementary. Linear pair theorem applies. So they're a linear pair.
Of course they are.
Now, if they're a linear pair by linear pair theorem, they must be supplementary. By definition of supplementary. What's the definition of supplementary?
Definition of supplementary equals to 180.
Yeah, the two angles sum to 180. So if they add up to 180, how much is left over for CFD?
It's not equal sign.
115.
I like act that out, man.
AFE, that's an angle down there. I'm going to do it in light blue. And AFC, like the football conference, right? AFC, we'll do that in dark blue.
Why is it not DFC for Derek's fried chicken?
Oh, man.
CFD.
It's CFD, baby. All right. So the dark blue and the light blue,
Derek's fried chicken.
they're a linear pair, yeah? Even though there's a thing that cuts them, it's still saying this whole angle and this angle. Do they make up the whole line? Yeah, they do, so they're a linear pair. Now we know that linear pairs are supposed to sum to 180 because they're supplementary, right? By linear pair theorem. Now we also know by angle addition postulate, if we want to know the big angle, we can add up the two small ones, right? So we add 65 and 65, we get 120 plus 10, right? Which is 130. And that means we can figure out the light blue angle, because how much is left over for him? 50.
50 cents. Put 2 quarters together.
BFE.
And DFC.
BFE is this angle. Big red. You don't chew big red? All right. BFE and CFD.
Continue.
CFD. Christmas colors. Red and green. They're vertical. Check it out. Ignore the thing that's cutting it in between. And we've got scissors, right? Scissor theorem. Those two angles are scissoring each other.
Your word's not
They should be congruent. Right? Because vertical angle theorem says they should be. Is they? Well, that's 115. What's the red altogether? 65 and 50? 115. Oh, yeah. They are indeed vertical angles. Yes, we can confirm this.
Oh, yeah. I can't see.
That's not my problem. Scoot closer.
You didn't see the board.
I think
You know what it says?
My reaction to everything you say is that SpongeBob meme.
Oh.
AFE,
Think about it.
Danny,
BFC.
do you have dreams about this class or something?
Of course not.
Very pointed question.
Yeah.
AFE is 50. BFC is this angle. So we're talking pink angle and light blue angle. Are they a linear pair?
I don't even
No, there's an angle in between them. Are they vertical angles? No!
I don't even remember what I drew.
They're neither.
You.
I never.
It says find measure of angle AFE. Well, we already did that. That's 50. I know you can't see it.
I can't.
DFC is 115.
Mr. Merrick, I can't see. I need your glasses.
BFC is 65.
Need your glasses.
Questions on that?
I'm gonna ace this now.
Dude.
If you don't feel like you're going to knock this out of the park, you need to come see me. Not so I can humiliate you, but so I can be like, hey, it's this easy. Let me show you why. And you'll go, oh, yeah, you're right. It is, actually. Even if you're completely lost right now. Seriously, I can teach you all this stuff in like 10 minutes. Come see me before school, after school, whatever.
You think you got your personality?
That's right. My homeroom's going to be packed today, by the way, because I've got Royer's kids in here, which are really my kids as well. She's just been having them in there instead of splitting them evenly. Yeah, you're going to be in here today.
So that means I should come.
What up? Yeah, you can say after school. I've got a little more time than usual. I'll be here past 4. Normally on Thursdays I got to head to DeKalb, but today I don't need to, as early at least. All right, define terms. Now we're almost done, right? Front page, transversal. Oh. I said this to the other classes. All right, guys, check this out. Check this out. This is a pair.
Oh, remember pair phones and Victorious?
That's a pair.
Yeah. Pair phones.
Now, a linear pair is when you squash that pair down and make a line. So I squash it and it squishes it. But the stem still's there. You know, the stem is still there. Let's use brown for the stem. But the stem is still there.
Show is called? Yeah.
Shut up, Danny. So look, it's a linear pair. I made it a line. That's a linear pair. It's a linear pair.
Blow it up. No, give it.
I don't get it.
It's a pair, but squished down into a line, so it is linear, and it's got a stem.
Use the film on Hyperbolic.
That's what a linear pair looks like.
I think this stem would have been squished down.
Because apparently when I tell you linear means line and pair means two, are there two angles on a line? It's not good enough to get you done. But like if you imagine the pair, now we have two angles on a line.
That is Mr.
Pair has two stems.
You're Spencer from
It has one stem. What are you talking about?
An apple would have been.
Oh, you're telling me if we have something like this with two stems, then it's not a linear pair? Yeah, now we have this. 1, 2, and 3. Well, 1 and 2 are not a linear pair, neither are 2 and 3. And 1, 2, and 3 aren't a linear pair because pair means two, right? These are all just collinear angles.
You used an apple.
Shut up. It wouldn't work. Pair, like, it's a play on words.
Then your apple.
Shut up.
You're Spencer from my college, you know that?
No, I'm not. You're crazy. I'm not crazy. You're crazy. Transversal. What's a transversal?
Making something opposite. Saying
It's a line. All right. A line.
Saying the opposite of what is true.
I feel like I could hear you all the way.
It's a line that what?
That's the two lines.
Cuts
I'm practicing my cursive.
two other lines.
I'm practicing my Norwegian.
If either of you don't get 100 on this, I'm just going to give you a 0. That's the new rule now. All right. Transversal, a line that cuts two other lines. Do the lines have to be parallel for it to be a transversal? No. This is a transversal. The green line. It's still a transversal. It's just not a very useful one, right? All right, cool. What's an example of a transversal in this diagram?
The one line that cuts horizontal.
Yeah, line T. Oh, hi. So you can either write T in cursive, because that's how we write lowercase cursive letters mean lines. Thank you very much.
Trash.
That was like a floater.
It was a floater.
Floor game.
Or you can just write this. Line T is an example of that. All right, let's go on to corresponding angles.
Oh, yeah.
I do not say it like that.
Yeah, you do.
That is not how I say it. I do not. Oh, yeah. You got to go up in pitch at the end. Oh, yeah. All right.
Now you sound like
Now I'm thinking about like old Mr. Lavelle and when he first used that. And I'm assuming it's not in class. All right. Okay. So anyway, corresponding angles. Angles that are. Shout out to Mr. Lavelle. Still kicking. Angles that. What? What are corresponding angles?
angles.
Are in the same what? Go ahead. The same relative position. Remember the abomination, right? If you're in the same position, that's gross. What we're talking about are things that are in the same relative position. Meaning if you look at their intersections, angle 1 and angle 5 are in the same relative position. They're both in the top left corner of their respective intersections. So, angles that are in the same relative. If you don't say relative, I'm going to mark it wrong and draw a monster. Relative position. I'm gonna do it.
See, so I can see your
What angles are examples of corresponding angles? Don't say 1 and 5.
draw monster.
4 and 8. Be careful how you say that.
Angle 4.
Okay. Same side, interior.
Why do you need to be careful how you say that?
That is the right question. Same side, interior angles. They're angles that, what?
Angels.
They're on the same side of the transversal, right? And what? Come on. The definition's in the name.
That are on the same side and interior.
They're same side of the transversal. Don't just tell me same side, right? 'Cause what does that mean, right? They're the same side of the transversal. They are in the interior of the lines that the transversal cuts. So I'm going to say angles that are on the same side of the transversal. you have something to say?
Yes,
Okay. On the same side of the transversal and in the interior of the intersected lines.
and interior. And are the
Again, same side,
That's a lot.
interior. Oh, get over it.
That's a whole class.
No one cares. Boo.
Limited or yeah.
You know how long it's gonna take me to learn all this?
I do not do requests. Alternate interior angles. Let's talk about those.
Where'd tissues go?
I don't know.
We
Not my
used
business.
all of them,
Yeah,
Peyton.
remember?
Yeah, it's last
Oh, I forgot about
Use
that.
your shirt.
Alt int angles. Hey.
Alternate interior angles.
You have to do more than one. You have to do it more than one person.
Angles that are. You drop something. What does alternate mean? Opposite sides.
Hey.
Opposite sides of the transversal. Be specific. That's impressive. And in the interior of the intersected lines, right?
Are you just gonna leave it there?
Yes.
I'm gonna go get it.
No, you're not. All right.
Yeah, sign it. You have to put that on the mirror.
Yeah, put it in the mural.
Okay, everybody sign it.
Opposite sides, alternate. Interior, in the interior. Right. Now, I'm going to save us all time. Alternate exterior angles and... Why is that not on there? Because I copied it from the other homework. All right, you should also write down not alternate exterior angles as well. We have same side as well.
I can't see what you're writing.
You're right. So make sure you know these and same side exterior angles. Sorry, I left those off there. I know. Just outright. Okay, so alternate exterior angles are going to be the same thing as alternate interior, except they're on the outside. So it's in the outside of the intersecting lines.
$5 and yours.
$5 is mine. I don't have $5. Okay. Also, I don't care. Sit down.
I gotta get the tissue box.
Smack you down on camera. All right.
You just typed in the box.
Yeah, that's okay.
Oh, I
I'm
didn't
not
know.
about the box. Didn't we have a lesson about that? Got to think outside the box. All right. Same side exterior angles are the same thing as same side interior angles, except they're on the outside of the lines that are intersected. So we did the entire review guide, pretty much. I mean, I didn't do these two. Do you want me to do 3 and 5 or no?
Are you gonna
Can I
repost?
check my expo card?
I'll do 3 and 5 real quick, and then we'll call it a day.
Are you gonna repost this on YouTube?
Repost? Everything's uploaded automatically. Yeah.
The two of you.
That is not what they call it, and for good reason. All right. Angle 1 is congruent. I'm on number 3. Is congruent to angle 5 by cap. Angle 5 is congruent to angle 8
That's all I'm gonna remember.
by vertical angles theorem. Right? And if we know that 5 is the same thing as 8, then we can switch out 8 for 5.
It's a you.
Ta-da! By subs. Swag box. 2 and 8 supplementary. I would say angle 2 and angle 4 are sup. And I know that by linear pair theorem. Then I would say angle 4 is congruent to angle 8 by cap. That's how I would do it. Therefore, I can switch those out, right? Angle 2 and angle 8 sup by substitution. Oh, swag box, you're right. Good idea. That's it. That's quiz tomorrow. That's the whole thing. It's going to be less questions than this. Knock it out of the park. If you can't knock it out of the park, come see me. That way you will. I can teach all of this, I swear.
Oh, really?
I feel like
Oh, really?
lazy on the first type of that.
It's a Thomas Schlaffer. What?
I feel like I'm just gonna be lazy on this.
Yeah, don't do that. How about you actually get it right and make sure you're thorough? The definitions are probably going to be the hardest part. Don't screw it up.
I know every other thing.
Well.
Okay? This is, as they say, a layup in basketball, which most of us it's easy for, right?
Unless your name starts with a D.
Unless your height is under 4 foot.
Unless
Okay.
your name starts with a D. Right, Mr. Matt?
That's that on that. Have I shown you why the area of a circle is pi r squared?
No.
Awesome. I'm going to show you some wholesome content.
Because a pi is a circle.
No, it's actually not. Pi is half of a circle.
I'm going to write this.
I
Sucks, but
warned
it's
you about
true.
the food.
Yeah, I know. Me too.
I should write all of this in error. So if I rip
You just
Don't
went
do
right.
it. All right.
I gotta think out of the box.
The word of the day is derivation. Derivation means to pull out of. Okay? Real learning, understanding, is pulling information out of something, being able to do that yourself. So we're going to derive the area of a circle, meaning why is the area of a circle pi r squared?
This is racism.
Writing's not that easy, but Grammarly can help. This sentence is
Don't staple
grammatically
your eyes.
correct, but it's wordy and hard to read. It undermines the writer's message and the word.
Pi r squared gives you the area of a
All right,
circle.
remember,
But where does
if you can't do it with the lights on, don't do it at all. We're keeping the lights on. Sit down.
pi r squared come from? First, we'll draw a circle and fill in its area.
I learned that in school.
Next, we will divide it into
Shout out to
logical
Mrs.
parts
Vance,
and arrange them in a rectangular
health
formation.
teacher.
As you can see, it barely resembles a rectangle. So next, we will divide the circle into small equal pieces, and we will arrange them in the same manner. You can see that it appears more like a rectangle. So, if we divide the circle into even more smaller pieces, you can see that every time the shape becomes more like a rectangle.
All right, so check it out, check it out, check it out. So if we divide the circle into pizza slices, right? We can slide those together, and the thinner we make those slices, the more cuts we do, the closer it becomes to an actual rectangle. And we understand the area of a rectangle. Base times height. How can it be anything else, right? So if we make a circle into a rectangle, we can figure out what the area of a circle is. Archimedes did this originally, and he figured out the formula, right? So when we cut this, the more cuts we make, the closer we get to an actual rectangle. Now, how many cuts are we going to have to make for it to be literally a rectangle?
600.
Infinitely many, right? Now, can we make infinite cuts? No, but we can theorize it, right? If we were able to do it, what would happen? Watch.
So, how small must we divide a circle before we can get a perfect rectangle?
Shaq.
Attack.
Well, we can keep on dividing the circle into small, smaller, or the smallest pieces you can make.
Danny size piece.
But the answer is to divide the circle infinitely many times until we cannot distinguish the lines, and eventually the circle can now become a perfect rectangle.
All right, so check it out. So here's what they're saying. They're saying that if we have a rectangle made up of
I understand.
pizza slices, right? What happens? What are the dimensions of the rectangle? Well, check it out. When we cut this open, right, we unfolded half the circle up top, half the circle down below, and then slid them together, right? So half of the circumference is up top. Remember, circumference is the perimeter around it, right? So half of that's going to be up here. So this is half of whatever the circumference is. Okay. That's the dimension up here. Now the side, well, is going to be the length of the pie pieces. Well, how long are the pie pieces? Half. The radius, right? Half the diameter, the radius. So this is r. Now, we know the area formula is pi r squared. They gave it to us earlier. Squared, I always remember the 2 goes up there because area is always squared, right? Feet squared, miles squared, et cetera, right? Circumference is the same thing, but the 2 is down here. 2 pi r. We can explain why that is later, but trust me on it. What's half the circumference? Well, half of the circumference is going to be what? The whole circumference is 2 pi r. So half is going to be 1 pi r. So this is pi r. What's the area of this rectangle? The area of the rectangle is going to be base times height. What's our base? Pi r. What's the height? R. the area of the rectangle is pi r squared. Now, how do we get this rectangle? From a circle. Which means the area of the rectangle is the same thing as the area of the circle. I always think that symbol's funny. And so the area of the circle has to be pi r squared. It's pi r squared. How can it be anything else? Archimedes first did this. What if we cut it into infinitely many slices? It would be a rectangle, perfect rectangle. Let's just imagine we did. Everything is a rectangle, and everything is a triangle, and all triangles are circles. We're going to get into triangles not next week, but the week after that. It's going to blow your freaking minds. We are eventually going to get into area, and we're not just going to be like, here's the formula for the area of a trapezoid, plug the numbers in, figure it out. We're not doing that. We're going to derive it. Why is the area of a trapezoid this weird, crazy formula? And if you know what it means, it's not going to be weird and crazy. It's going to make sense. Same thing with this. You're going to have to derive the area of a circle. Well, it's not hard. Take the circle, cut it in half, right? Put it together. Pi, r, and r. Base times height. Everything is a rectangle. All rectangles are triangles. All triangles are really just circles. It's like a rock, paper, scissors game. Let's watch the rest of the video.
Your words, not mine.
That's right.
So, the area of the circle is equal to the area of the rectangle, which is equal to base times height. The height of the rectangle, as you can see, is the same as the radius. So, height is equal to radius. To find the base, we need to look at the circumference of the circle. And when we compare the base and the circumference, we can see that the base is equal to 1/2 the circumference.
This guy's voice is amazing.
Remember that the circumference is equal
It's one of the first
to
videos I ever
2 pi
watched that got
r.
me into math, actually.
When we combine it with 1/2,
When you know what it means, it's
the
interesting.
2's cancel out, and base is equal to pi r. So now, base times height becomes pi r times r. Combine the r's together, and we have pi r squared, which is equal to the area of the rectangle, which is equal to the area of the circle. So pi r squared can be used to calculate the area of any size circle that exists.
Rate, comment, and subscribe. I don't know what rate means.
Like 1 to 10.
Means like comment like what you think.
What you think the video?
Yeah, like I would rate you 1 out of 10.
Nice, nice. 1 out of 10 would watch again, right? That's the rhyme. There it is. How much time do we have left? I went through that pretty quickly. We get out of here 39.
Yeah, play a song of the day.
A song of the day?
Play a Blueface song.
I don't think I'll do that. What I will do is I'll show you this.
Do
let's go to the 3 blue,
Gold
1 brown.
Digger song.
The full title of this video.
3 Blue 1 Brown is an excellent channel. You should definitely watch it. We're not gonna have time for a full video, but I will show you something that's interesting.
Wait, what is the name?
Let's see. Vectors, matrix, multiplication, essence of calculus, neural networks, geometry. These might be a little bit outside your scope. Let's find something a little bit more basic. I just don't want to overwhelm you, and it's a short video. We won't get, it's only a short amount of time, so we won't have time to really get into it.
I think 3 million subscribers.
I wanted to tell you about the maths of my new tattoo. So I got recently a tattoo. This is a hyperbolic helicoid, and so I was going to explain the math of helicoids and a little bit of hyperbolic space. So I actually went into the tattoo parlor with the line work and the shading, and I had an artist who was kind enough to actually transfer that onto my body. I wanted to make sure it was mathematically correct. So one of the things about it is that helicoids are something that showed up in my PhD an awful lot, and I'm an aficionado of hyperbolic space, anything negatively curved, so I combined them and made a tattoo. This is my first tattoo, but may get more math tattoos in the future. So helicoids are a type of surface that's called a ruled surface, a type of surface that is made entirely out of straight lines. So I've got straight lines that are displayed here, and I can change the number of lines on the surface, and I've got other parameters that I will be changing throughout. So one thing you'll see is there's this opacity here. So this is showing the full surface. So I can turn that on so you can see a bit of surface and see how it's being filled up with lines. This here is going to be the simplest ruled surface you can possibly have, is the plane. It's just created with a whole bunch of straight lines. So I can just continuously fill it with straight lines. This is the hyperbolic paraboloid. It's also called a hypar surface. I'm gonna basically sort of twist up the ends of these. And so this is my parameter here I call height. So as I stretch it, I end up with this surface here. So this is something you see in architecture a lot. This is in a lot of roofs. Actually, you see a lot of ruled surfaces in architecture because it's very easy to get straight objects, and then it's just about the way you assemble them that gives you curvature. They're all still straight. Everything you do about them is straight. So the next one I'm going to show you is a hyperboloid of revolution. So what I'm going to do, this has 4 lines now. I'm going to continue to add lines in. This makes it a cylinder, and I'm going to turn on my surface. So there's a bit of surface back here. So what I'm going to do is each of these lines, I'm going to twist it right about here. And that is going to start moving it around, and it will become